Let's move on with the next hand rules. So if you try to look at the video, if you forget, you can try to watch the video again, how we can use the left hand rule, Fleming left hand rule, which if you remember, the first finger, which is a thumb, is F, second finger is B, the middle finger is I, and usually at the beginning when we learn about it, it is going to be used to apply on a straight wire with an external B field, and that wire may be moved, alright, depending on the setting. At the same time, you may also apply the same hand rule, which is the left hand rule, on the charged particles. That means it could be electron or proton sometimes, right, for the simplest case, and they would also experience a force when they enter the magnetic field. For example, you may have, let's say, I can draw it here, that you have some B field that is pointing towards the background, so these are the B field, and let's say there's an electron going in, like this case, going to the left. This is the velocity. Think about when this electron enter the B field, this electron will change the direction because there is an external B field. At the same time, the movement of the electron would actually cause its, will be taken as the current. So if you remember the I, conventional currents that we usually talk about, and the movement of electron, they are in the opposite direction. That means when the electron moving to the left, in this case, the current is actually going to the right. So if you try to use your left hand, you can try to take out your left hand now. Use the usual way that we do, like this way, and you should find if you point the middle finger, because it's FBI, so the middle finger, sorry, not middle finger, the second finger pointing into the paper, which is B in this case, and then the I going to the right direction, then you have your thumb pointing up in this case. So this will be the direction of the force experienced by the charge in this case. And if you remember the usual way that it does is, since the electron will be going up in this case, then by the time it go up like this, then you can see that the current has been changed already, because since you are moving up, imagine there's more B field here, then this movement going in this direction, maybe I use a blue to show the pattern, to show the path, alright, in this direction, then the velocity at this point will be going more like in this direction, in this tangential direction. But then once again, the current is in the opposite direction, so that means the current is actually pointing backward. And if you try to use the left hand rule again, with the B field unchanged, also pointing into the paper, you should find at this spot. So if the electron is at this spot moving up, that means the current is going down, then the force will be going to the right, and so on and so forth. If you continue to think about what will happen next when this electron start to move in such a curve in this way, then the force at this point will be pointing downward, same as this one. Okay, and that actually means when the electron going into the B field, it will perform a circular motion, and this is something that we will learn later on. We will use some more calculation integrating what you learned in chapter 6 to do some questions. So here's the idea, and in terms of the force experienced by this charge, now we will tell you there's an equation to calculate the magnitude, because in year 10 we just tell you the direction. So here is the equation, and you will find the equation, which is B is the B field magnetic field, referring to the magnetic flux density, You could also call it as magnetic field strength also. Alright, like how strong the magnetic field is. And as you can see from the equation, that will be equal to F over QV times sine theta. First of all, Q over here, maybe let me zoom in. Right here, it will be simply refer to the charge in Coulomb. Remember, not one single charge in Coulomb. So if you have only one electron, then you have to convert to charge by looking at the data booklet. So if you have the data booklet, you can try to see that would be on an immense charge here. So 1.6 times 10 to the power of negative 19 Coulomb in that case. V will simply be the velocity in meter per second. While you may find it will be a bit strange to see the trigonometry function sine theta here, and I'll explain that in a second, why there's a trigonometry function here. Okay, so this is how you can calculate the force in Newton. And since the textbook also mentioned that the word B can be called as magnetic flux density, I would like to introduce you an idea which you can find in the link also for this website, again, Hyperphysics. When we talk about B field, all right, there's a B you can see here, and when we talk about the word magnetic flux, later on we will use it also, is the amount of B field that you receive in a particular area. And this is an illustration. For example, you have a certain area. It could be the area enclosed by the coil. If you remember, you learned about motor and generator, and there is a coil inside, and that could be the area enclosed by the B field. Because only the B field inside the coil are useful. Outside of the coil, they have no effect at all. So that's why we have to multiply A usually, since B is like the density. And so what about the angle then, you may ask? When there is a B field going in a certain angle, remember when we do the hand rules, all this has been 90 degrees. So what if they are not 90 degrees? Then they simply would be weaker, you may think. The worst cases is when B field and current in the same direction, which is also mentioned in the textbook, is that if the charge is moving along the B field direction, there will be no magnetic force. Because simply think about when you try to make your fingers in 90 degrees, there's no way that the direction could simply be parallel. In that case, there will simply be no force. So in that case, then we have to use some trigonometry to find a component. Of course, in parallel situation, we just simply treat it as 0. But what if it is at a certain angle? Then we have to take the component. That's why we introduce the idea of trigonometry, sine or cosine theta. In your data booklet, they will tell you that it is, actually I don't remember, let me take a look. They would tell you, oh, it is sine theta, but I would say the reason why I would not remember is I don't actually use this equation. What I mean is, you actually never know whether it is sine theta or cosine theta always. That means you have to refer to the situation and see whether or not you should take sine or cosine, because depending on which angle they give you, they may give you an opposite angle, and actually you have to use cosine instead of sine here. So let's say I could make an example that is, if say there is a certain B field going in this direction, and then the current I going in this direction, you can imagine it's a proton simply, if you want to make it easier, because proton is positive and the direction of velocity is the same as the direction of current, right, to make it simple. So there is a certain angle you can see, and what you should be thinking is that, so should I simply take sine or cosine or what? Again, it is not safe to simply say sine or cosine theta, because it depends on the angle that they gave you. They may give you this angle instead of this green angle. So it depends on which one they give you. Then they may give you, that would have a different equation in that case, depending on which one you use. The easiest way, or I should say the best way, the safest way to do is imagine this velocity has two components. So one is going in this direction, the other one is going in this direction. Alright, so one is, you can say horizontal and vertical in my picture here. Which one do you think it is responsible for the magnetic force? And that's something that you need to think about. Which one is responsible? If you try to think about what we just talked about earlier, that if the velocity and the B field are parallel, then that velocity would not be generating any magnetic force to you. So in other words, this velocity is useless, right? We would not count that. We will not account for the force. The only force that we will, velocity that we will count is the vertical one in this picture. And so in that case, you should think about, so would this be V cosine or V sine theta then? Alright, and that is the question you need to think about. And apparently it should be, let me see, it should be, if this is theta, then this is 90 degree and this is 90 degree minus theta 2. So I think it should be, if this is the angle and this is V, then this is cosine, V cosine 90 minus theta, so theta 2. So in that case, that will be V sine theta 2 in this case. Yeah, okay, so that would be how you could deduce it if you try to do it more carefully. On the next page, you will find, well, this is a rearranged form of the previous equation. Both are fine, and you will find the one on the data booklet as in this one. Alright, I actually like this one too, so you can stick with this one. And if you try to look at the second half of the page, you will find there are multiple versions of hand rules. You can see there are A, B, C. They also explain to you version A, version B, version C, and how to use that to determine the situation that we just talked about, a charged particle going into the B field. If you are interested, you may want to take a look, but I would say if you already understand what we have been using for IGCSE, it may be just the most convenient and secure for you to stick with the approach that we've been doing so far. I know later on when we talk about the right hand Fleming rule, some people, they will try to use the same hand. So instead of left hand and right hand, they use the same hand to deal with all the situation. And that is also possible. But then once again, since you have learned it in year 10, then I would recommend you to just simply stick with that. Otherwise, you may sometimes find it confused and you may make mistake in that case. Alright, and if you're interested in maths, and especially if you're an Excel student, then you may want to pay attention that when we try to do just now the formula, this is more like in terms of magnitude. We calculate by magnitude, and the direction we just determine by the usual way that we learn using hand rules. But if you are trying to express it more properly in terms of vector form, then we'll be using QV times cross B in this case. And if you learn about more deeply in maths, you know B cross QV is different from this one, right? And that actually will give you an opposite direction. If you don't understand this part, that's actually fine. And now what I would want you to do is 2 examples on the question note. So you may want to pause the video and try these 2 examples. Okay, so first question is asking you to express Tesla. Actually, Tesla is the unit for B field, magnetic field strength, and you actually express it in the fundamental unit. If you recall what is fundamentals units again, let's just try to recall, right? There are 7 of them. If you really want to challenge yourself, you may want to pause the video. They are kg, meter, candela, Kelvin, mole, what else? Mass, length, time, second. 1, 2, 3, 4, 5, 6. There should be one more. I can't remember also. What is it? Oh, current. That would be ampere. Okay, so that would be the 7 units. All right, just think about all the topics that you learned in physics. So what to do next is you have to use formula to relate them. So simply using the formula that you learned, which is F equals to, if you can take a look at the data book, QVB. For the sine theta, you can negate that for now because we're just taking care of the units, and apparently that one doesn't have any unit. One thing to remind you is that I have mentioned before, but in a case where you want to present the idea of unit of something, you may use a symbol of this, right? This bracket. And if you try to bracket F, then you may say, oh, the unit is Newton. That means if you somehow just simply write F equals to N, this is terrible, because we can't say force equal to Newton. You can say force equal to, say, 10 Newton, 1 Newton, 3 Newton, but you can't say force equal to Newton, because Newton is the unit of force, but it is not force in itself. But what you can say about is, you can say unit of, again, this means unit of, F equals to Newton. At the same time, it equals to Q, which is in terms of Coulomb, V is meter per second, and B is Tesla. Okay, so once we get this, then we can try to rearrange it so that we can have maybe Tesla T equals to Newton divide C meter times S in this case. And since you can see on the right hand side here, these are not fundamental units. Remember, these 7 will be fundamental unit. So what you have to do is further kind of dissolve them into fundamental unit. For Newton, if you recall that is actually F equals ma, you can make use of that. So kg meter per second square, and the second I'll keep it. Coulomb actually is the idea of charge, and if you remember, for current is charge over time, so that is ampere equals to Coulomb per second. So Coulomb, I would and in that case Coulomb is ampere times second, so AS in this case. And for meter, it is simply fundamental units. I'll keep it as meter. So for now, I will simply try to cancel out the same stuff. So S got cancelled out, and M got cancelled out, and I think that's all. So the remaining units will be kg second -2, A -2. Oh, sorry, -1 in that case, and that should be the answer. Okay, next question is said there's a bar magnet, and which direction of force is on the electron. So the hint actually is given that to ask you to draw magnetic field. So if you once again remember how to draw magnetic field is from north to south. So north coming out to south, so it looks more like I don't know how you call it, butterfly maybe, something like this, and it should be symmetrical, although I know I didn't draw it very symmetrical in this case. So this one will be going to the south. You can imagine there is much bigger one going around this whole globe and back, coming back to this. Alright, like this. And if you try to draw over the electron, then you could draw something like this, north to south, like this. And apparently you can see now that on top of this electron, then the magnetic field is going in this direction. Alright, towards the left actually. So it said the electron approach a bar magnet, so that means the velocity is going in this direction, and while B field is going to the left. If you recall once again, maybe I try to erase some of these to make it easier to see, then velocity, because this is electron, is opposite to the current direction for electron, so I is going this way. And since you got I and B, then you can find the direction of F. Now what you want to do is take out your left hand, record the three fingers as FBI. B is going to the left, I is going down, so you should have your thumb pointing towards the paper. So towards paper I would draw as a cross, and so the answer is for the force, it is into the paper. So this is how you determine the direction.